You open a Python dictionary and look up a key. It returns instantly. You search a database for a user by ID. It returns instantly. You type a URL and your browser already knows the IP address. Instant. Every one of these operations is powered by the same data structure, the hash table. And yet most developers cannot explain why it is so fast. Today we are going to fix that. We will build a hash table from scratch in our heads, walk through every mechanism that makes it work, and understand why it achieves constant time lookup regardless of how many items it stores. Imagine you have 1 billion user records and you need to find the one belonging to Alice. With a plain array, you have to check every element one by one. In the worst case, that is 1 billion comparisons. With a sorted array and binary search, you can have the search space each step, which gets you down to about 30 comparisons. That is better. But a hash table does it in 3 operations regardless of whether the table has 10 entries or 10 billion. O of 1, constant time. The key insight is that instead of searching for data, we calculate its address directly. We transform the key into a number, and that number tells us exactly which slot to look in. The component that makes this work is the hash function. A hash function takes any key and converts it into a large integer deterministically. Give it the same input twice and you always get the same output. Simple hash for strings might multiply the running total by 31 and add the ASCII value of each character, all wrapped with modulo arithmetic to keep the number bounded. That large integer is then reduced to a slot index using modulo by the number of buckets. Hash of key modulo bucket count equals your slot. The two critical properties are determinism and uniform distribution. Deterministic means the same key always lands in the same slot. Uniform means keys spread evenly across all available slots, rather than clustering together. Under the hood, a hash table is just an array. We call each position in that array a slot or bucket. When you store a key-value pair, the hash function tells you which slot it belongs in. When you retrieve a value, the hash function tells you which slot to look in. Consider a table with 8 slots and 4 entries. Bob is at slot 2, Carol at slot 4, Dave at slot 6, and Alice at slot 7. To retrieve Alice's score, hash the string Alice, take modulo 8, land at slot 7, read the value. 3 operations, that is it. The size of the table does not matter. Whether there are 8 entries or 8 million, the lookup always takes the same number of steps. Here is the uncomfortable truth: sometimes 2 different keys hash to the same slot. If hash of Alice modulo 4 equals 3 and hash of Zara modulo 4 also equals 3, we have a collision. 2 records cannot physically occupy the same slot. There are 2 main strategies for handling this. Chaining stores each slot as a linked list. When a collision occurs, the new entry is appended to the list at that slot. Lookup walks the list until it finds the matching key. Java's hash map uses chaining. The second strategy is open addressing. When a slot is occupied, probe the next slot and the next until you find an empty one. Python 3's dict uses a variant of this with pseudorandom probing. Chaining is simple and handles many collisions gracefully. Open addressing is faster in practice because it keeps all data in the same contiguous array block, which the CPU cache loves. Collisions are rare when the table is mostly empty but become common as it fills up. This is measured by the load factor, the number of keys divided by the number of buckets. When the load factor exceeds about 70%, collisions multiply and performance degrades. The solution is dynamic resizing. When the threshold is hit, allocate a new array that is twice the size, then reinsert every existing key into the new array. That reinsertion step is called rehashing. It costs O of M work to move everything across. But here's the important part: because the table doubles each time, this expensive resize happens only logarithmically often. If you do the maths on all insertions combined, the amortized cost per insertion is still O of 1. This same doubling trick is why dynamic arrays like Python lists and Java array lists also achieve amortized constant time append. Let us be precise about the complexity guarantees. Average case get, set, and delete are all O of 1. Worst case O of n when does worst case hit. When a bad hash function sends every key to the same slot, the table degrades to a linked list and every lookup scans the whole structure. This is not just theoretical. Attackers have exploited predictable hash functions to cause denial of service by crafting inputs that all collide. Python responded by introducing SIP-hash with a randomized seed per process, so an attacker cannot precompute collisions. The load factor threshold also matters a great deal. Python dicts resize at about 2/3 full. Java hash maps default to 75%. Lower threshold means faster lookups but more wasted memory. Higher threshold means denser tables but slower when clustering forms. Hash maps are everywhere you look once you know what to look for. Every variable lookup in CPython goes through a hash table. The globals dictionary, the locals dictionary, class attribute dictionaries, all hash maps. JavaScript objects are hash maps. When you write dot notation or bracket notation, you are doing a hash table lookup. Database systems use hash indexes for equality lookups, giving O of 1 retrieval for queries like where id equals 42. PostgreSQL, Redis, and DynamoDB all expose hash-based storage. Your browser maintains a DNS cache as a hash map from domain name to IP address, with TTL handled as a timestamp field. Compilers store every identifier in a symbol table implemented as a hash map, so they can answer in constant time whether a variable has already been declared in the current scope. Let us put all the pieces together. A hash table is an array of slots. A hash function converts any key to a slot index deterministically and uniformly. When two keys collide, chaining or open addressing resolves the conflict. When the load factor exceeds the threshold, the table doubles and rehashes. The result is O of 1 average lookup, O of n worst case when the hash function fails, and amortized O of 1 insertion. The structure powers Python dictionaries, JavaScript objects, database hash indexes, DNS caches, and compiler symbol tables. It is the single most widely used data structure in production software precisely because constant time lookup is transformative at scale. Understanding it not just as a black box but as a concrete mechanism changes how you think about software performance. That is hash tables from first principles to production. If you found this useful, the next video covers B-trees, the data structure that wins when you need range queries rather than exact lookups and powers the default index type in every major relational database. Subscribe so you do not miss it. Thanks for watching.